Our final lecture in this lecture series is basically an introduction to dynamics and to nonlinear problems. I think it would be good for everyone, having seen these lectures, to realize what the extension of this course would be. Now, linear dynamics is perhaps the most easy extension, particularly the eigenvalue problem, that is the normal mode problem, because that literally only involves adding about 5 cards to a static data set in order to get the normal modes of a structure. A second area, though much broader, is that of nonlinear problems, and there you can have all kinds of weird nonlinearities, material and geometric and boundary condition. So we'll talk about these two extensions in turn. Let's consider dynamics. Really, this is what would be called structural dynamics. And what we want to do is take our same linear structures that we've been solving, but apply some time-dependent force. This will make the whole system jiggle and oscillate and add a lot of interest to the structural response. Now, basically you have this expression for displacement field now, where this is the field displacement, and I mean it to be written or understood as a function of time. Likewise, the nodal coordinates become functions of time. The kind of interpolation that we did before to find the field displacement as a function of the nodal displacements now is written in a separation of variables form, where the spatial dependence is separated from the time dependence. And this isn't obvious. It's one way to do it, and it turns out to be very robust. In other words, as long as your elements are small, this really works. And the separation of the space and the time problems helps us to solve many, many structural dynamics problems. The one limitation is that within a single element you have synchronous motion. That is, every point within an element will sense what's going on at all of the surrounding nodes and will immediately react. Therefore, if you have propagation problems where they're wave-like events, you have to have enough small elements so that the lag in response can be accomplished element to element and doesn't need to be accomplished within one single element. In linear structural dynamics, the character of the response is often governed by the character of the loading. Let me sketch 5 possible types of loading here. First of all, the harmonic load. Now, that would be a sine wave, say, acting on a structure, and I'll use red for the force that's acting on the structure. Then the response for a system at rest might follow a curve that would initially be perhaps not sinusoidal, but with time probably will become a true sine wave with some lag in response. Periodic problems are where you have a forcing function that itself could be Fourier analyzed and broken into its components. So this sawtooth wave might have a certain amount of energy in each of the several of these sine waves. Then the response can be found in a series form. Transient problems are where you have a sudden spike of force, let's say. This could be an automobile hitting a curb or an aircraft hitting a sharp-edged gust. The response here would be that typically the structure, depending on the frequency response of the structure, would receive enough of a boost that it would do some kind of motion afterwards. If there were damping in the system, then this would die out in time. The fourth case that I mentioned is stationary random loading. This would be characteristic of turbulence acting on the lift of an airplane's wing. Many of you have had rough airplane rides and you know how that can happen. Luckily, this is rather straightforward to handle, and you do it in a statistical way by average response due to average random force characteristics. Lastly, I show a truly random loading, and that's impossible to handle because you cannot even predict in the future what it would be like. You could do this in an experimental way by measuring such a load pattern and then doing a simulation over the time. And an example would be if you bought a pair of shoes and they were sitting on a shelf for a while, for a time, and then you walked home with them and kicked tin cans and scuffed them and so on. Then at home you took them off and set them down, and perhaps someone turned on a hot plate nearby and heated it up, and then it cooled down, and so on. And a truly random force field is really difficult to characterize just because of that true randomness. And generally speaking, people will choose the worst portion of an expected forcing character such as this, and then do perhaps a stationary random study of this region, let's say, and then a deterministic study in some other region if they're able to break the loading into such pieces. The systems that we study can be of several types, and they can exhibit several general classes of response. This is distinct from the loading that we showed earlier. For instance, the system itself could involve rigid body motion, or it could involve elastic motion, or a combination of the two. For instance, a vehicle rolling on a highway, such as this one on the left, is showing rigid body motion. And there are many courses in universities for vehicle performance that really limit themselves to rigid vehicles. For instance, in the aeronautical area, if you're looking at flight mechanics and you study the mode called the phugoid mode, which is a long-term longitudinal mode of motion, that is done by assuming that the aircraft is rigid. And similar things would happen in the automotive area. If you were interested perhaps in gasoline mileage and their hills and valleys, you probably would assume a rigid automobile. On the other hand, many fields will have bodies that are restrained, and the only way they can move is through elastic motion, as shown on the right. And this means that the body as a whole cannot translate or rotate freely. There are combinations of the two. One of them that has come up in aeronautics in the last 10 years has been something called a body freedom flutter, where for many years people had studied the wing as if it were purely an elastic motion leading to what has been called wing divergence. But in recent times, at least two people have shown, no, indeed, if you consider the way that the fuselage can move up and down, that the airplane really will suffer a kind of flutter before it hits the wing divergence. So there was a case where the failure to include both types of motion led to really the wrong results. All right, now another thing that one might consider besides those system characteristics is whether you're going to look at the body's motion under purely a forcing function that is externally applied, or whether you're going to look at the body under its own self-generated motion. These are generally called forced vibration and free vibration, and I think that distinction is pretty obvious. There is a borderline case that causes me some trouble in teaching this, and that's the case of a body that has been displaced initially and then allowed to respond by its own internal forces. Is that a forced response, or is that a free response, a free vibration? Well, every free vibration indeed needs some kind of a start such as that. So, but on the other hand, many people would like to view that as a force vibration problem if you're really going to look at it, especially in the transient case. So I think you have to tell from the context of the problem whether a displacement-controlled initial condition is to be viewed more as a free or a force vibration. It won't be a problem for us in this little discussion. I'd like to show the equations of motion for systems, and I'd like to show it for the forced vibration and then the free vibration. Most dynamics problems that are discrete can be posed in a matrix form such as this, and you will have a mass matrix that characterizes the inertia forces in the problem, and a damping matrix that will typically act on a velocity term, and then a stiffness matrix, which we've looked at closely before. So we've already looked in the linear static problem at this pair of terms here, except that we've now made the forcing function a function of time, which is new. In total, this is called a response problem because, generally speaking, your attention starts at the force on the right and then you move to the left and you wonder what kind of a response will you get in the displacement, velocity, and acceleration. Now, if we want to study the so-called normal mode problem, it's a kind of free vibration. Then we're going to arrive at what is called an eigenvalue problem. And we get that by setting the damping 0 and the external force 0. So in the above problem, I will knock out this middle term here and the right term here. Now you're left then with a balance between the stiffness of the system and the inertia of the system. And this has become a specialized problem, an eigenvalue problem, where you get self-maintained motion. You'll find that the energy alternately trades back and forth between kinetic energy due to inertia and then the potential energy or strain energy here due to the stiffness of the body. The form, if you assume a response that's harmonic so that there's a spatial distribution of displacements at the nodes, let's say, times cosine omega t, you will then get this equation below where the omega comes out because of the two derivatives and forms this problem that's often called the general eigenvalue problem. I'll further break down those two mathematical problems into these subcases. In the response problem, which involved the forcing function, you can deal with frequency response. It has to do with harmonic loading typically, or a periodic function that can be harmonically analyzed. You can deal with transient response, which typically involves numerical integration in time, or you can deal with statistical approaches with random response. And many computer programs will handle all three of these. Certainly, most of them will handle the first two in finite elements, and then the third one, even when it's handled, is handled with different degrees of success because it's somewhat of a specialty area. Now what I found is that the automotive and aircraft industries do a lot of work in frequency response and some work in transient, and then the missile industry does a lot of work on random, and I think that has to do with the noise field from the rocket engines. Now the other math problem is the eigenvalue problem, and typical conventional structures with placid loading that we're used to would form the real eigenvalue problem and require a real eigenvalue analysis. But if you have exotic loading such as follower loads or aerodynamic loads, usually fluids flowing over a structure will cause complex eigenvalues, and that means that you can get motions that are not just happy to be self-balancing in time, but rather will grow in time or subside in time because of energy either being put into or taken out of the system. There are three structural matrices of interest in the equations of motion: the mass, the inertia, and the stiffness terms. It's ironic that we spend a whole term studying how to do the stiffness matrix, and the mass matrix can actually be covered in one lecture. And then the damping matrix is sometimes just assumed in the blink of an eye, often by past experience. So there are problems that are actually dominated by the damping matrix, which is the one that we often so quickly assume. And problems such as the resonant response of a damped structure actually have resonant amplitudes that are inversely proportional to the size of damping, and so it's very important there. Well, let's talk about these three matrices and see if we can get some intuition for what they are. First of all, we're used to studying a finite element, but for the moment let's concentrate on an infinitesimal element shown here, dx by dy by dz. Now, you might not have gotten this feeling, but it is true that if you move a particle of material in an elastic structure some distance, that the opposing force you will generate will not be collinear. Now, you would have gotten that feeling already had you seen things such as I-beams that have typically a greater moment of inertia through their depth, let's say, than through the width. And this would literally happen, that if you displace this body at 45 degrees, you're going to find the restoring force trying to push back against you will be not at 45 degrees, but at some other angle. And so I think that the development of this stiffness rate matrix here really is a serious contribution and did take quite a bit of time. And you may want to remember it in this context, that this is why it's difficult. Damping and inertial forces do turn out to be collinear with the respective velocity and acceleration vectors at a point. Everyone agrees that if you have an acceleration as shown here to the right, that then you will get the reversed effective force shown to the left. That idea was popularized by D'Alembert. Of course, this stems from Newton's second law that F equals ma, and so no one worries at all today about the validity of this little element of mass here. On the other hand, for the damping force, if we show the direction of velocity of that particle, people are in agreement that the damping force should oppose the velocity in a collinear way. Showing up here is this vector quantity, but there's a lot of disagreement about the kind of damping to be used, and which means the magnitude of this set of coefficients here. Now, what I've shown is a kind of viscous damping that's proportional to volume. But for structural mechanics people, there's a more popular form of damping, and interestingly, this square boxed coefficient is actually set proportional to the size of the elastic force that we showed on the previous figure. And so that's the most useful kind of damping in structures problems. I want to introduce you to a very powerful idea called the consistent mass matrix. Now, this will take us several figures, but when you get done, you're going to see probably the most important single piece out of an entire structural dynamics course in finite elements. What we do is use our previous knowledge about equivalent nodal loads for external body forces. And we had an expression shown here that came about directly from the use of virtual work. What this did was convert a distributed body force into a set of equivalent nodal loads that had the same effect on your system, or at least as close as possible under this energy formulation. But we know that using the D'Alembert idea, that this volumetric body force could be given as a density times the acceleration of the body. And I'm actually going to combine terms shown here then. I want to go around the shape function. And this comes about directly from our D'Alembert interpretation of inertia forces. Now, This is the field variable form on an infinitesimal volume element, but we can now discretize over a given finite element. And we use that separation of variables argument to show that if the displacement field can be interpolated this way, then you can take a derivative of both sides, and it will affect the field variable here, of course, but only the nodal variables here become nodal velocities. Likewise, the field acceleration is a function of the nodal accelerations. And luckily, the shape functions, because they are only functions of space, are very placid in this operation. Our equivalent nodal load expression originally had a body force. We then converted that to a relation to the acceleration field. Then we gave a way to discretize the acceleration field, which depended on the shape function matrix. When we insert that, we then get this term here, the n times the nodal displacements. We now are in the position of having one shape function that helped distribute the loads properly, and then another one that helps interpolate the acceleration field. Indeed, this becomes what is known as a quadratic function that way. And we name the part of this quantity that lies in the integral the consistent mass matrix, and give it the symbol m. At the element level, I'll use a lowercase m. And we now have a matrix for inertial forces. The damping matrix can be just stated outright as B times the velocity vector for the nodes, and then there are assumptions that are made on that B matrix. There are a number of interesting models. There is a Rayleigh damping, where you can make the damping proportional to how much mass there is, or a little bit proportional to how much stiffness there is. Then there's the structural damping. Then there's some even wilder dampings that are really nonlinear, a Coulomb or a Stiction, and some other kinds. Generally, though, we would use linear damping laws in a linear structural dynamics problem. Now, in all of our statics work, we concentrated on this much of the equation. We now can add these newly found equivalent nodal loads, both the inertia and the damping loads on the right-hand side. But it's been more or less a convention to put the highest derivatives to the left in a set of differential equations, and so it's very typical to bring this mass term far to the left and then the damping term next to that. But we know how this equation was really derived. Let's look at an example of a consistent mass matrix, and I will take that one for the Turner triangle. Here it is, and it's not a diagonal matrix as a competing philosophy called the lumped mass approach is. And what this implies is that there is inertial coupling between the different degrees of freedom in the element. In this case, it will turn out that for a Turner triangle, that if you accelerate one node, it will cause forces at all three nodes. And they will be in the ratio of 2 to 1, that you'll get 2 parts of reversed effective force at the node that's being accelerated, and then 1 part at each of the others. And you can see that effect in the matrix, where there's a stronger diagonal effect. So there's somewhat of a localization that when you accelerate a given node in a certain direction, that the reversed effective forces are greater at that node than at the remote nodes. And if you add these masses up sometime, if you're curious, you'll find what might be disturbing, namely that there's twice as much mass here as the triangle actually has. But you see, that's because the total mass opposes the motion in the x direction, and the total mass opposes the motion in the y direction. And so there's always such a factor. And were this a three-dimensional element, the total consistent mass would be 3 times the actual mass of the element. Let's spend a few minutes on dimensions and units. This is really important in structural dynamics and causes a lot of trouble, more than you would think, especially for people just learning structural dynamics. There are basically two systems. One is gravitational, the other is the absolute. Now, structures people generally use this one, and then fluids people generally use this one. That just seems to be convention. I don't think there's any fundamental reason. Furthermore, although the System International convention is to use Newton meter second, it turns out that finite element people pretty much around the world are using Newton millimeter second. And when you pick a small length scale, it causes a corresponding large scale for mass, so that the megagram is the mass unit then, and that's a metric ton. Something similar happened in the English system, namely that the convention was normally to use pound-foot second, but many people in structural mechanics use pound-inch second, and that led to a mass unit called the slinch, or slug inch, and which was quite a large unit of mass. The fluids people are pretty much dealing with the larger length scales and deal either in metric or in English. To this point, all of our problems have been linear, and this means that we've been moving up and down on a straight line in the load deflection curve. What can go wrong with this? Well, if this is a load deflection curve shown here, then what can happen is that as you raise the load, you can hit a situation where either your point coming up this straight line will reach a bifurcation and will do something disastrous, or you may get a jump from that down to a point on this curve. A number of bad things can happen. But the fact that there are possibly more than one solution as you look at the cause up into the effect, and here I'm showing three, that's a definite indication that you have a nonlinearity. This is covered by Kirchhoff's theorem, Kirchhoff's uniqueness theorem, that says that if you have linear material and a linear strain displacement law, and if you have uniquely posed loads, then you'll get a unique answer out. So such a system would by definition have to have a nonlinearity in it, otherwise it would be contradicting the Kirchhoff uniqueness theorem. Now on the right I've shown a different kind of relation though, here where it's a parametric relation, where on the horizontal axis I've got a frequency, not a load, and on the vertical axis I've got a kind of a displacement. And this would be a frequency response curve, so-called, in dynamics problems. Normally this would have a single unique value in a linear system, but nonlinear systems can have such things as this detached solution branch. You can have such a thing as a jump where the system will fall off that peak and jump down to a lower energy state. So those things are characteristic of what goes bad in a linear system. One of the favorite cartoonists in the United States is Gary Larson, and he often does cartoons such as when amoebas go bad, and I kind of wish I could get him to do a cartoon on when finite elements go bad. He'd probably do a good job. Well, that's what our problem is here, that our linear finite element theory is going bad. And how are we going to understand that? First of all, where does it go nonlinear? If we write out our familiar vector mappings that we've had, we have laws, we have physical vectors such as strain, we have operators. Now I've put in red here the three major places where nonlinearities really originate. And these mappings, the strain displacement law and the stress strain law, or you could call it the constitutive or material law, are subject to becoming nonlinear. Likewise, the boundary conditions in the case of interference and contact problems can go nonlinear. So really it's in those specific areas, things such as equilibrium are still just adding up forces. Compatibility is still just making sure that things connect properly. And displacements are still measuring the motion of particles. So they're not the primary source of the nonlinearity. These red mark things are. The three sources of nonlinearity can be discussed in turn. The constitutive law would be such a case is shown here for a nonlinear material where you have a softening behavior. Other materials might be hardening. Some plastics lock up as the little chain molecules link together and lock. The strain displacement law, as you go to large displacements, you start violating some of those small slope and small deflection assumptions, and ultimately you can get behavior such as this bifurcation, where you might have a system buckle. In the boundary conditions, you can have contact problems, such as the footprint area of a set of wheels on an airplane that's landing. Now, how broad a footprint that is would depend how much of the weight is being taken off the wings and transferred to the wheels. So as the airplane slows down, presumably the footprint would get larger because the wheels would carry more of the weight. Interference problems are common, where you'll have two bodies bump each other. And you see, these problems are difficult to set up a priori because the boundary condition depends on the current solution that you are thinking about, and so therefore it is a true nonlinearity. I'd like to cycle through those three kinds of nonlinearities again. We'll start with nonlinear material problems, and think about the tensile tests that you did back in your mechanics classes. You often were asked to take a cylindrical specimen, say of mild steel, and then pull on it and watch the load deflection behavior until the specimen broke. In the large, it's a softening behavior for mild steel, carrying less load proportionately to the deflection as it undergoes larger and larger strain. But if you interpret the stress as the current load over the current cross-sectional area of the neck down region, you might find that actually the material itself was hardening due to strain hardening. So the details of how you measure, how you interpret results in nonlinear problems really are more fussy. When I was an undergraduate, I had a machine shop class, and I tried to form a chamber for a pulse jet engine by welding two pieces of stainless steel together. But I needed to flare the tailpipe to meet the combustion chamber. And so I heated both the stainless steel tubing on the right and then a plug that was a solid steel plug red hot. And then I drove the plug into the tube opening and flared it as shown. It was really going beautifully. The stainless steel was flaring just as soft as butter. I decided to stop and check the dimensions and measured and found I was short of the goal, and then I heated things up again and tried to drive the plug further. No luck. Absolutely rock hard. The stainless steel had hardened in some way due to the quenching in air of just cooling it, and I couldn't get it to flare any further, no matter how I heated it. I didn't know enough about materials at the time to really do this well, but it stopped my project, it turned out. So I appreciate now how materials can lock up in such situations. A professor friend of mine, Al Weinman, once worked out a procedure where he could study the material properties of the dura mater, which is the covering of the human brain. It actually means tough mother in Latin. And he developed a test with a circular disc that was inflated from one side. This brought out the nonlinear character of both the material and the deflection of the disk. So it really is a little tougher problem than just nonlinear material, but brings in both nonlinearities. In any event, he was able to back out the material properties for the dura mater. The inflation of the membrane and having both geometric and material nonlinearities is a lead-in to this next figure where we do want to look at geometric nonlinearities. Suppose you have an unstretched wire here and then a bird lands on it. Naturally, the wire will deflect, and it does so because it can carry load in the deflected shape. In fact, the deeper that it deflects, the stiffer it will get, such that if two birds landed on the wire, it wouldn't deflect twice what one did, and likewise 3 and 4. And you would find then that this would be a hardening system in which we could put the number of birds here on the horizontal axis and then the lateral deflection on the vertical axis, and you would find that that curve would not be flat but would be some kind of a hardening nature. Now, another nonlinear problem is that of Euler buckling, and this again is due to geometry, not material softening. If you take a slender body, shown here, and load it axially, at some critical load it will suddenly snap and will bend over. Now, if you control that load by a test machine, for instance, which won't allow the structure to completely fold up, you'll find that you really haven't damaged the material. And so you can relax that situation, you can relieve the load, and the structure will spring back to the initial shape. When I was teaching an undergraduate lab, we were able, if we were careful, to buckle the same column several times. Now, ultimately, you start rounding some of the corners and you affect either the boundary conditions or the load application, and the system sometimes isn't completely repeatable after several loadings. But the point is that you aren't damaging the material, but you are suffering a loss of stability because of the geometry going bad on you. Our last source of nonlinearities had to do with boundary conditions. And a typical contact problem that I'm pointing out here would be the case of a mill van that I once studied. And these are these large trailer boxes that are carried over the road when wheels are attached, or the wheels are taken off and the body is attached to a flat pallet for airlift. The military uses these a lot. Now, after they've been run over the road on wheels, they develop a bow, which I'm sketching here and perhaps exaggerating, so that when the clamps are put at the ends to try to force the trailer flat, then you have to develop quite a force. So I was asked to predict that force as a function of the initial bow, and it turned out to be quite a hardening system shown here. The reason it is because as you pull this down flatter and flatter, basically more and more of the undersurface of the mill van contacts the pallet. And then one way to think of it is that you're progressing from a cantilever beam, if you look at the right half of it, with that length to a cantilever beam with indeed a shorter and shorter length, and it becomes stiffer and stiffer. An interference problem would be that of a beam that has a pin at the end riding in a slot. And while this beam is in the centered position, it acts as a cantilever beam. But if it's deflected far enough to the right, let's say, such that the pin bottoms out on the end of the hole, then you'll get basically a clamped pinned beam behavior. And I show that at the right. This is an example of what is called piecewise linear problems. And these will often come up in the contact situation. This concludes our lecture series on linear static finite elements. It's been a pleasure presenting these lectures to you, and I hope that they'll be a help to you in your career.